Okay. All right. Let's continue on the lecture on state space model. Okay. All right. So in previous lecture we looked at so-called canonical format already. So that we call that case number 1. So we looked at the control canonical. Okay. Let's look at the second case today. We'll look at observable canonical format. So basically, we have the same starting point . Okay, so same starting point at here. Missed. So here is the general Gauss transfer function expression. So here's the general one. Okay. So we'll look at how we manipulate this one, and then so that we can end up with basically an observable canonical form. Okay. Yeah. There's my lecture notes. Okay, I'm going to use the same. I'm going to use the same example as we did in the previous lecture. So use the same example that we did for the control canonical. Here is that system. I'm going to rewrite the system in here. Okay. Okay, suppose this is the pulse transfer function system. Okay, and we're going to try to derive a state space model based on this one. Okay. Now, from here, okay, from this system and here, I'm going to rewrite the system. Okay, in terms of basically this input u and the y at here. So I'm going to rewrite this one. So basically, what you do is you multiply the y with this denominator, and then multiply the u with this numerator at here. Okay, yeah. Okay, so this is what happens after you multiply this y and a u like that. Okay. And then I'm going to manipulate this like this. So you multiply the y into the bracket, okay, into this bracket here, and also multiply the u into this bracket. Okay. And then you move, okay, this. The rest of the term except the y over z, move all of the term to the right side here. Okay, move everything to the right side. Okay. moving everything to the right side at the same time. So we're gonna do this at here. So no, so there's really no very good way. Okay, let's try this. Okay, so here you have a z, okay, to the power -1, and then 0.5 times u of z, right? So this is this term here. Okay, yeah. And then here you have a -0.6 times y of z, and then there's a z to the power -1. So this term over here. Okay. Like it? Okay. And then let's keep moving. And this is a z to the power -2 times u of z. And then here is z to the power -2. This is negative here. 0.5 times y of z. So this term, right? Multiplied by this is this. And then last term, which is minus that 0.3. Here's z to the power -3, and then y of z. Okay. So if you see here, I have a sort of a counterpart for each pair, right? So u of z, this is z to the power -1. This y of z, this is z to the power -1, right? So this is z to the power -2, z to the power -2. So I'm gonna try to make it the same counterpart here. So basically, what I'll try to do is, let's say I have a z to the power -3 times 0 u of z. Okay, yeah. So nothing changes. Add a 0 term, and then minus that z to the power -3, 0.3 y of z. Okay, so now from here, okay, we're gonna further manipulation at here. Okay, I'm gonna take this z to the power -1, this common factor at here, okay, out of these two terms at least. So then I have 0.5 u of z, and then minus 0.6 y of z. So far so good? Okay. And now this term here, okay, these two terms, there's a common factor z to the power -2, right? Common factor z to the power -2. So if I have a common factor to the power z to the power -1 here, I can use another z to the power -1 here, and then here is u of z minus 0.5 y of z. See, right? So this z to the power -1 multiplied by this z to the power -1, you get a z to the power -2, and that multiply into this one here, you get these two terms here. Okay. And the last one here, we're going to apply the same thing. So take another z to the power -1 out. So, and the last one here is, this is basically 0 times u of z, and then minus that 0.3 y of z. Okay. So you see that, right? That's like a nested structure at here. Okay. Yeah. So the inner cell of this nest is this one, and it keeps going out. Okay, so this is sort of like a nested structure, right? Yeah. So your y of z, okay, basically is equal to this whole chunk right here. Good. So now once we get this now, and I'll draw a simulation diagram from here now. Okay, I'll draw a simulation diagram. So draw the simulation diagram based on this structure. And this structure right here, there's a name called, it's actually called nested programming structure. So basically, if you're going to, it's like a different, if it's a difference equation, if you program it in your controller or somewhere else, and you're basically programming like a nested structure. Calculate this first, and that, add it together, and add this together, and then you get the output here. Okay, yeah. So what's the let's say take a look at what would be the simulation diagram look like for this particular structure right here. Okay. So first of all, we have u of z. Okay, control input u of z right here. Okay. We also have. So I'm going to draw a line here representing this is my input u of z here. Okay. And then I'll draw another one right here, which is my output, okay, y of z right here. Good. So let's start from this inner cell right here. Okay, this inner cell. So the inner cell has 0 times u of z right here. So I'm going to just draw here, and this is basically 0, right? And this is 0 in here. And 0 times this, and then the output right here is 0.3 times this output, right? So we can output a 0.3 right here. Let's put a negative 0.3, that's okay. Yeah. So where is that multiplication? So it comes from the output here, right? Yeah, so the output times this negative 0.3, the input times 0, and then you add these two together, right? You add these two. So this structure here, realize this inner cell right here. And then the output of this will be what? Delayed by one step. Okay, so z to the power negative 1. So that's this portion here. That's this portion. And then this portion will add with this plus this. So that's another u of z times. So here's like you have a 1 at here, right? 1. So basically you can grab a signal from the input. Okay, grab the input from the signal from the input here, then times 1. And then grab the output times negative 0.5. Okay, so grab the output times this, and then all these three, add them together. So 1, 2, 3. Right. So that gives you this bracket here, right? This bracket, okay, this half bracket here. So good. And then the results of that will get delayed one more time. Okay. So you keep going, then you can see now. So the last step, you have a 0.5, and then here is negative 0.6. Finally, everything get delayed one more time, and you finish that book, right? Yeah. So here is basically the simulation diagram based on that nested programming structure. Is that good? Yeah. So once we have this simulation diagram now, if you recall from previous lecture, then we will start to pick our state variables, right, based on the simulation diagram. And if you recall that what I mentioned in the previous lecture, which location that we typically use to pick the state variable based on the simulation diagram. That's right. So you have a location here and here and here, right? So that's basically the location you pick your state variables, or you pick your states. Then you probably have a question. So I have 3 states, right? Then which one should I call it x1? Which one should I call it x2? Or which one should I call it x3? Right? So typically you can see this is you can call it this x1, x2, x3. But you can also what? x3, x2, x1, right? Yeah, so you could also do that. Either one is fine, actually. Okay, you'll end up with just the matrix slightly different, but it's the same, basically describing the state system here. So I'm gonna, in my case here, I'm gonna let this one x1 of k at here, and then here I'm gonna let it to be x2 of k, and here to be x3 of k. Okay, yeah. So once I have this now, then I can basically use my previous. So if this is x3 of k, then here must be x3 of k plus 1. And if this is x2 of k, then this must be x2 of k plus 1. And this must be x1 of k plus 1. So now you have your x of k, you have your x of k plus 1. Then we're ready to write down our state equations, right? Relating the k plus 1 term to the k terms, basically. Okay. So let's look at this structure right here. Let's start from here. So let's take a look at x1 of k plus 1. Okay. So x1 of k plus 1, what does that equal to? Follow the flow of the signal. Here is x1 of k plus 1. So what does it equal to? That equal to 0 times input plus negative 0.3 times the output. But output here is x3 of k, right? So basically negative 3 times x3 of k. That's your first state equation. x2 of k plus 1. So x2 of k plus 1. So that equal to 1 times this u of k here. Right? So this u of k plus negative 0.5 times x3, and then plus this x1 of k here. Right? So there's 3 signals here. So x1 of k here, and then minus 0.5 x3 of k, and then plus u of k. If you follow the flow of the signals, this is the second state. This is the second state equation. The third state equation, x3 of k plus 1, and that equal to what? Equal to x2 of k plus minus 0.6 x3 of k, and then plus 0.5 u of k. That's it. That's the 3 state equations describing the k plus term and the k terms. So now you can write this whole thing into a matrix format. So one side is your x of k plus 1 vector, which is x1 of k plus 1, x2 of k plus 1, and x3 of k plus 1. And then this one equal to the matrix times your x of k vector and plus matrix times the input u of k. So based on the state equation here, right, you can easily put the fill in the blanks for each row. First row here, right, give you x1 of k. So first row times this column give you x1 of k. So you have d here. Coefficient must be what? 0, 0, negative 0.3. Second row here times this column give you the second state equation. So it's 0, 1, negative 0.5. Here's 0, here's 1, and last term here is this is 1, 0, right? Yeah, and 0, 1, and here negative 0.6, here is 0.5. Okay, yeah. So that is the state equation for based on this nested programming structure. Okay? And this is basically what we call observable canonical form. So this is your A, and this is B. So the matrix A at here and B here is in the observable canonical format. Yeah. The control canonical. Yeah. Very good. So I'll come to that. Yeah. Now, later we'll look at why is it called the control and observable. Okay. So let's write down the output equation in here. So output equation, and output is just simply just x3 of k. So that's just 0, 0, 1, and then times your x of k vector. Okay. Yeah. So this is your C matrix. Good. Right. So as Simon was just observed there, and so I'll probably just write down. This is just a very important observation. Okay. If A, B, C, D. Okay. So the four system matrices. Okay. If they are in control canonical format, okay, it's just like what you derived in the previous lecture, right? Then, okay, and then what? Then A transpose, C transpose, B transpose, and then D. Okay, and they are the observable canonical form. So that's a very handy tools you can actually make use of, basically. So if you already derived control canonical, then if you're required to write it in the observable canonical form, you can use A transpose, replace the A, use C transpose, replace the C, replace the B, and use the B transpose, replace the C, and you get your observable canonical form. Good? Yeah. So now you can already see, right? You can see now. So basically, if given a g of z, right? So how many types of discrete state space model? How many types of discrete space model that you can use to derive based on this g of z? How many? Three? Infinite. Yeah. Right. Yeah. They're infinite. Basically, if you have g of z given, you can literally derive an infinite number of discrete state space model based on the given g of z. And you already see there's these two popular ones, the control canonical and the observable canonical. Okay. In the next lecture, when we learn similarity transformation, that basically explains the infinity solution there. You can use any type of similarity transformation, and you can transform this system to completely different appearance, right? But they're still describing the same g of z, which is the same system. Okay. Yeah. Now in MATLAB, okay, so this is actually where you got to be careful here. Okay. So in MATLAB, there's one way you can do is this. You define a numerator. Basically, let's say you have a g of z, right, equal to numerator divided by denominator. So you can define your numerator, you can define your denominator, okay, based on the given g of z, and then you can define, let's say for example, your sampling time, okay, yeah, and then you can you can construct yourself a transfer function, okay, based on this numerator, denominator, and the sampling time. So this will give you the discrete g of z, basically. So this will give you this g of z here, right? Okay. And once you get this, you can use a command called transfer function to state space. So transfer function to state space, numerator and denominator. Then you can have A, B, C, D, okay, return from this function here. So that'll give you basically, in this case here, it'll give you actually the control canonical. Okay, it'll give you the control canonical here. Good. But there's one thing I need to warn you, basically, using MATLAB to create a state space model. Okay? So when you're using the MATLAB tool to create a state space model, there's one uncertainty, is you don't know what the state variables the MATLAB presents. Okay? So it gives you this control canonical format here, but not necessarily it's the type of states that you wanted to choose. Which means what? For example, I have a mass spin damper system, right? And I wanted to choose two states. One is position, the other is velocity, right? Because I have two sensors probably to measure the two states. Okay? Yeah. But if you use a MATLAB tools, or any other tools to derive a state space model, because there are infinite number of solutions, right? So mathematically, you can choose an arbitrarily or completely unrelated, unrelevant mathematical states. Not necessarily it's the position, it's the velocity. You know what I'm saying, right? So you pick two states for you. It's just mathematical states, right? And then create a state space model basically for you. Yeah. So that's the uncertainty when you use a tool. And you not necessarily, the system not necessarily will give you the states that you want. So that's why a lot of time you actually manually, I will show you one example shortly, manually derive a few steps first, and then you use the tools to help you establish a state space model. Okay? Yeah. So just be careful with using the MATLAB command in here. Okay? So let me just see another type of format here. Okay, it's called Jordan canonical form. So this format at here basically will present the A matrix. So basically the A matrix at here is a diagonal matrix. Okay, that's the idea of the discret here. Okay, so I'll show you an example and to see how it works. Yeah. So now I'm going to use a slightly different pulse transfer function. So let's say I have a pulse transfer function, which is this one. Now, if you look at this one here, and you will see that if you let the denominator equal to 0, you'll see that this system basically has two poles and two real poles, negative 0.9 and negative 0.8. Okay. Then from here I can use a partial fraction expansion for this system in here, so we can get a partial fraction expansion for this system. Then I'll write it into this filter format. Alright, so this is the system here. Now I can build a simulation diagram, okay, based on the addition of these two terms at here. Okay, so let's see how can I build a simulation diagram using the two expressions. Okay, so input is u of z, and then output is your y of z or y of k. Okay. Yeah. Now, if you look at each one of the term here, okay, if you look at each one of the term here, even just look at one of this. If you look just one of this one here, so each one of them are basically in the what type of format? Each one of them is basically in a format like this. So g over, so this one here, right, is like a g over 1 plus gh format. So, right, so the top and the bottom here, like a g over 1 plus gh format, right? Yeah. So in this case here, you can see the g here, let's say maybe is z to the power -1, right? So maybe I should say, just look at this portion. Okay, forget about the 10 here. Okay, just look at this portion here. So this portion is in this format: g equal to z to the power -1, and h equal to what? -0.9, right? Yeah. So if you have a transfer function like a g over 1 plus gh, so if you recall that, this is actually a very common closed loop control system. Input g in the forward loop, and then h in the feedback loop, right? Yeah. So when you have a feedback system gh like that, your transfer function is g over 1 plus gh. Okay. So I'll make use of this result set here to construct the simulation diagram. So you have this term in here. Basically, you have basically a loop right here, and then g is z to the power -1, and then you got a feedback right here as h, which is -0.9. Right. So that's one small loop right here. Another one here, the other one there is z to the power -1. Here is -0.8. So negative feedback. Okay. So that's the two. These are the two loops at here, right? The two components. Cool. Yeah. So if I'm going to derive the output, you can see this u times this portion and times that portion, right? So basically u goes to here and here. So u goes into both of this. The results that are here, the first one you need to time that with a 10. The second one you need to time that with a -10. And once you get these two now, then you add these two together, plus, and that's your output right here, right? Yeah. So this is your simulation diagram, basically. Okay? Yeah. Once you get your simulation diagram, and you can pick the states. So I can pick states here and here. X1 of k, X2 of k. And then I can derive my state space model now, right? So here is your x1 of k plus 1. And here is x2 of k plus 1. Then x1 k plus 1, x2 k plus 1. So what does that equal to? Alright, so let's see. I'll skip myself a little bit here. Okay. I'll let you fill it down here. So what would you get for the blank matrix A and B? Go through this flow of the signals using the simulation diagram. Yeah. Yeah. Right. See, that's a diagonal matrix. Right. This A matrix diagonal, and this is one here, one in here. Okay. Yeah. What's the elements on the diagonal? What's the value of the diagonal elements right here? Poles, right? Yeah, that's right. So this is the Jordan canonical format. It produces a diagonal A matrix. The A matrix is usually the most important part. Diagonal A matrix and diagonal elements are the poles of the system here. Okay. Yeah. So, and you can derive the output equation, which is 10, -10 here, and then times x1 of k and x2 of k. So this is this one is actually a simple example. We can spend a little bit more to a little more complicated case. Basically, if the pole is, let's say, if one pole actually repeated twice or triple times, right? Yeah. Then the Jordan diagonal matrix, okay, is actually going to be in more of a block diagonal matrix. So, say for example, right? For example, let's see you repeat it twice. Okay, yeah. So, and then maybe you have another one here, another one here, for example. Okay, yeah. So you may end up with this Jordan canonical format for this one here is, so you have a 0.3 here, then you have a 0.2 at here, and then over here, right? Over here you have a basically 0.51, and then there's another one 0.5 here. So it's a block diagonal matrix. Okay? Yeah. Yes.
Can I just ask you a question about your diagram?
Sure. Yeah.
So in your A matrix, you have negative 0.1. But just like in the feedback there, I noticed x1.
Oh, this should be positive,
yeah,
right?
okay.
Right? Is it? No, it should still be negative. Because my H here is negative. Yes, it should be a negative feedback. It should still be negative feedback. Because my H here is negative 0.9. So H here is negative 0.8, negative 0.9.
Right, but when you write up the states basically, then isn't it x1 times negative 0.9? You can use that and subtract it.
Oh, is that right? Just a second here. Let's see, is that right? x1 of k plus 1 equal to what? Equal to yeah, you're right. Oh, there's again a minus here. So is that a mistake here? Just a second. Oh, sorry. Yes, this is a mistake. Who said negative? Simon said negative. Yeah. There's no mistake here. Huh? Yeah. Because the pole is at 0.9 and 0.8, right? Yeah. Okay. Good. All right. So that's Jordan. So let's just only consider the three cases. That should be enough. Okay. Yeah. So most of the time when you're in exam, you're not going to have a too complicated transfer function to derive. And then also this step, for this kind of step, typically you'll use formulas later instead of going through all the details, simulation diagram, all the detailed derivations. Okay, so I can a little bit summary it here. Then before we move on, what we have done is, we have a bigger picture here. Okay, so you start with g of s, okay, and then g of s can be converted into g of z using zero order hold. Okay, using zero order hold equivalent to obtain g of z, and this is the part that we have just practiced. from the g of z, we got our discrete state space model. Right. So this is there are three cases, three types that we covered. Okay, the three types we covered here. Right. Yeah. So now, for the next part of the topic, I'm going to go through a slightly different direction, or slightly different route, but end results are the same. So we also want the discrete state model. So we'll start with the g of s. So then from here, we're going to, from g of s, we derive the continuous state space model. Okay? So if you have a g of s, we can derive the continuous state space model. From a continuous state model, this is basically the portion in here. We use some kind of a discretization method to obtain a zero-order hold equivalent. Okay, discrete state space. So this is basically the next part of the topic here. How can we go from a continuous one state space model to a discrete state space model? Okay. Okay, so that's the idea of the next part of the topic here. I'll use a very simple example later. So for this part of question mark, this one should be quite easy here. So from here to here, so leave that to temporary. Okay? And actually, if you learn model control, then you should be able to derive. So going from g of s to continuous state model, that should be fairly simple. It's this portion, so we're going to focus on this portion right now. Suppose you already have a continuous state space model. How do we discretize that to obtain a zero-order hold equivalent discrete state space model? Okay? Yeah. So the idea is basically to discretize. So discretize the continuous state space model discretize the state space model here. Okay, so I'm going to write down the continuous one first. If you have a continuous state space model, let's say it is in this format here. Here is a continuous state space model with a certain given matrix F, G, C, D, and then the objective is to obtain a discretized state space model. So this step here basically is a discretization. The whole point that we're going to cover is how do we discretize it to end up with a zero-order hold equivalent discrete space model. Okay. Yeah. First step. Okay. So I'm gonna have to jog your mind a little bit right here. Okay. So first step is we're gonna have to start from this continuous state space model first. And we'll look at what is the solution for a continuous state space model. Okay, so here you have a model, here is a continuous system. So I'm trying to derive the solution based on this. This essentially it's a differential equation here. Okay, this is essentially it's a first order differential equation, right? So to jog your mind here a little bit, in second year system dynamics, okay, we have been we tried to solve different type of differential equation, and this is the first one we tried actually, first order differential equation, right? Yeah. So why do we review this portion here is because if you look at the state space model, the continuous state space model, which is basically what? Which is basically x dot here minus that f x over t and equal to g times u over t, right? So if you look at this one here, it may look different. So this is a vector, right? This is a vector, but it's still first order derivative, right? And this is a matrix. This is a function. That's fine. This is a matrix. This is just a single scalar quantity, right? Yeah, but in terms of formality, you see the format? Okay, it's the same format, right? Yeah, same format here. So if you have a first order differential equation, how do I solve for this one here? I'm not sure if you recall that. We have a so-called what? There's integrating factor methods. Okay, there's integrating factor method to solve it. Okay. So for this integrating factor method, what do you do is you multiply both sides of this equation with an integrating factor. We call that sigma. So you multiply sigma to both sides of this equation. Multiply sigma both sides of this equation. So the sigma here is the so-called integrating factor. Okay, integrating factor. By introducing this sigma here, then the whole left side, okay, the whole left side here, you can somehow rewrite it into this derivative. Okay, so basically, the whole left side is the result of this applying the product rule. If you apply product rule of the sigma y prime, what do you get? You get basically sigma prime y plus sigma y prime, right? Yeah. So you already have a sigma y prime here, sigma y dot here, and in this portion here is your sigma prime y, right? Yeah. So you see. So for this portion here, so this is basically equal to sigma q of x like this, right? Because this is basically sigma y dot plus sigma dot y. Okay, for this one. So you already have a sigma y dot. So all you need is to let this one equal to the sigma dot y, right? Yeah. So that basically meaning you have sigma here, sigma prime or sigma dot, sigma prime, okay, sigma prime equal to this sigma p of x. Okay. Did that jog your mind to a long time ago? So from sigma prime equal to this, now we have, this is basically d sigma over dx, right, equal to sigma p of x, right? Yeah. Multiply the dx to the other side, you get the d sigma equal to sigma p of x dx. Okay. Yeah. And then we can integrate both sides. Okay. Integrate both sides of this equation. So for the left side, integral of d anything, right, give you back the sigma. Sorry, hang on a second here. Oh no. So I'm gonna have to divide the sigma over this side here, right? Because sigma and sigma is together, right? Yeah. So divide the sigma to this side here, so this becomes 1 over sigma. Okay. So 1 over sigma, integral 1 over sigma d sigma, that equal to the integral px dx side here. Okay. Yeah. And what's this side here? This is what? Ln sigma, right? Ln sigma. And this side here is just, let's keep it px dx here. Okay. So that gives us overall the solution for sigma, this integrating factor, which is e to the power of px dx. Okay. So this is basically, in this case, the sigma is function of x. Is that good? Right? So that when you have a first order differential equation, okay, using the integrating factor, you get that integrating factor is e to the power of integral px dx. Okay? Yeah. Now coming back to this one here, okay, coming back to basically we're going to use the same method to solve this question here, right? So you can see this negative f corresponding to which one? To the px there, right? To this px. Okay. So if I'm going to use the integrating factor methods at here, then what is my integrating factor for this particular case? Is sigma equal to e to the power of integral, integrating what? Px, but now you're integrating negative f and then dt, right? Okay. So that's the integrating factor for this particular question. Now f is a constant. We're talking about linear time invariant system. So the f at here for the continuous system is a constant matrix. So this is a constant here for this integral. So that you can basically take this out of this integral at here, and which you end up with just simply e to the power what? E to the power negative f of t, right? Yeah. So this is the integrating factor for this system here. So now we're going to say, okay, we're going to multiply this integrating factor to both sides of the equation. Okay, so you basically multiply the sigma here, and a sigma here, which is this term, e to the power negative f t. So e to the power negative f t times x dot t minus e to the power negative f t times f x of t equal to e to the power negative f of t times g u of t. Good. And with the integrating factor, this appropriate integrating factor here, now the whole left side will be able to be written in this format, right? So that equal to e to the power negative f of t times x of t at here. The whole thing take a derivative, right? Take a derivative here. And this equal to e to the power negative ft times g and u of t. Is that good? Yeah. And the left side here is a derivative. Basically, I'll just, instead of write this one here, it's a d over dt, right? It's a d over dt. Okay. So I'll multiply this dt to the left side at here. Okay, so multiply dt to the left side. So this side is just d negative ft x of t equal to e ft g u of t dt. Okay. So then integrate both sides, right? Integrate both sides of this equation now. Integrate both sides. Integrating both sides, we integrate from t naught to t. Okay, so we integrate both sides from t naught to t. So starting point, assuming it's a t0, maybe it's a 0, right? And end up with a general t there. Okay, yeah. And let's take a look at the results of this integral now. So this side is integrating. The integration d anything is antiderivative. You get the results here, whatever in that bracket, right? So basically here you get e to the power negative f of t x of t, plugging the limits t naught to t. Okay. And then the other side, we'll just keep it for now because we don't have all the information. Okay, yeah. And plugging this limits at it here, right? Plugging the limit. So this side here, you plug in the limit. This is what? E to the power f of t, x of t. So you can plug a t here, and then plug a t naught. Right? Plug in the t naught, which will be this one here, right? And the other side is t naught to t. Okay, to this. Okay. Now I'm gonna move this term to the same side, to the right side there. So basically, that becomes this, right? It becomes this. Good? Yeah. So we're almost there. Now, the last step, So you're solving, remember we're solving for solution x of t here. So now I'm going to divide both sides for this term, right? Divide both sides. Dividing both sides for this term basically means you can multiply both sides by e to the power ft. Okay? So that'll get rid of that term there. Okay? So multiply e to the power ft here and e to the power ft here. Then the solution give us this x of t. Okay. So this side here, when you have a e to the power a multiplied by e to the power b, it's e to the power a plus b. So this is basically e to the power of f t minus t naught, right? Yeah. And here is x t naught. And then here is e to the power of ft at here, so let's just keep it. Okay. This is basically the solution. So here is solution, but I'll write down one more step over here. This is basically you get the solution for original continuous state space model. Okay. One more little bit the manipulation in here. So if you look at the second integral, this integral right here, okay. If I look at the inside here, if you recall this t, what do we call that? It's the what? Dummy variable, right? The dummy variable here. Dummy variable meaning you can use any variable you want. But right now, see the results here, this is t naught to t, so that at the end this integral comes with a t function, right? The t function here. But I don't want to duplicate it because I already got a t at here. So I'm gonna basically replace this t with a dummy variable tau. Okay? So we can replace this with a dummy variable tau at here. So there's nothing changed. Okay, it's just changing this dummy variable from t to tau. Cool. With this little change, okay, now you can see I can actually bring this e to the power ft into this integral now. Okay, into the integral. Because this integral is about tau. Okay, it's not about t. So the t e to the power ft here for this integral can be considered as a constant basically, right? So you can bring this into that integral, then it becomes e to the power f, so t minus tau, and then g u of tau d tau. Okay. There. So this is the final format that we want for further calculation. So this is the solution. Okay. Here's the solution starting from x t naught and end up at x of t. Right? So this x of t naught at here, so we call that, sometimes we call it what? Initial condition, right? So if you have a state space model, you apply initial condition, and you could actually just no control input, or you could have a control input. Right? If you don't have a control input, then you get basically a transient response with respect to a certain initial condition. If you have a control input, then you get a controlled input, a control response for a system, right? Yeah, good. And a couple of things, important things that are here. Number one, this e to the power ft. Okay, so the e to the power ft at here. And if you recall that, what do you call this matrix? This is f is a matrix, right? F is a matrix. So exponential to the power of ft still end up with another matrix. Okay. So this one in here, if you recall, that is called state transition matrix. Okay, state transition matrix. It's very easy to understand. So because this is the matrix, right, e to the power of ft, are the coefficient or the multiplication with the initial condition x over t naught, right? So here is your initial state. Here is the final state. So considering if you don't have any control inputs at here, so this whole term is 0, right? Yeah. Then the final states are being carried or transitioned to the final here from the initial to here, and the whole thing depends on what? This e to the power f of t here, right? Yeah, so that's called transition, state transition matrix. And this e to the power f of t, if you apply Taylor series, you basically end up with addition of infinite number of terms. Yeah, so that's your e to the power f of t. You can also apply some calculus operation to this e to the power f of t, and that gives you very much like a typical derivative operation. Okay, yeah. Okay, so once we have the solution now, right? Remember the objective is to discretize this continuous one into a discrete state space model, right? So now let's look at the actual objective now to get this so-called zero order Hode equivalent, okay, of this x of t to obtain a zero order Hode equivalent for this continuous space state space model. So how do we get zero order Hode equivalent? But first of all, we have to think about the idea of discretizing it, right? Discretizing it. So I'm going to consider a very simple case. I'll consider I'm going from tk moment to tk plus 1 moment. So considering the system response from tk time moment to tk plus 1 time moment. So, okay. And I will purposely let the duration of these two moments to be one sampling time. Okay, to be one sampling time. Good? Yeah. So now, essentially, if you look at the current consideration in here, so this is like starting from tk, right, and end up at tk plus 1. So basically, it's like starting at a t naught and end up at the t, which is the solution we have just derived. Make sense? Yeah. So we're going to do a very simple replacement. Essentially, we're going to replace the t with tk plus 1, replace the t naught with tk. Okay? Yeah. So if I do this one here, I get x of tk plus 1. Okay, we replace that t with this tk plus 1 equal to e to the power of tk plus 1 minus tk, right? So that's originally this t minus t naught times x tk, then plus the integral. The integral, instead of t naught to t, it will be tk to tk plus 1. And here's e to the power of f tk plus 1 minus tau, okay, and then g and here u of tau and d tau. Okay. Let's simplify this a little bit here. And here you happen to have a tk plus 1 minus tk, and as we said, we purposely make these two different by a sampling time. So this becomes e to the power of f times sampling time, right? So remember this is sampling time t, okay? And then times x tk at here. Okay. Now for this integral, okay, so let's not touch the integral here. Let's just keep it as is. So this is simple step here. Okay, so that integral, just keep it here. Now let's go back to this idea of the zero order hold equivalent. Zero hold equivalent. So what does zero order hold equivalent means? So you see, first of all, U at here is what? Is the control input, right? Is the control input. So zero order hold, if you recall that, when you have a zero order hold at here, and you have a system, you have a control, let's say you have a signal given to the zero order hold, and what comes out of this zero order hold basically what? If whatever input value at here, it'll do what? It'll keep that signal by a sampling time, right? Keep the signal by sampling time. So if I have, let's say, right now you have a control input to the system, and you have a zero order hold. So that basically means if this is a tk, if this is tk plus 1, then the control input between this tk to tk plus 1, it will always be capped at which value? The control input to the system. tk, exactly, right? Yeah. So you have the previous, you have the current basically calculated control inputs, and you're trying to fit it to the system, but you have a zero order hold there, right? So basically the signal over here will not change, right? So this is the signal over here will not change between this tk and the tk plus 1 time instance. It'll be capped at the value u of tk there. That make sense, right? Yeah. So then this u of tau at here, this is basically the next step now. So let me write this one here. So e f t x of k x of tk, okay, tk, yeah. And then here's tk plus 1. Here's e to the power f tk plus 1 minus tau, okay. And then this u of tau, right, which is basically the value between tk and tk plus 1, will be capped at tk here, and then d tau, right? D tau. Is that good? So take a second look at this expression here. So this is the integral with a dummy variable tau, right? With dummy variable tau. And this term g is a constant term, right? It has nothing to do with tau. And now this u term becomes a constant value now, right? Also has nothing to do with the tau now. So these two terms, you can take it out of this integral now. So now you can take this term, take these two terms out of the integral now. Okay? Yeah. So let me put this one here, x of tk plus 1, right? This is x of tk plus 1 equal to this. So now with this result set here, right? So then let's do this. For tk, so let's consider this is basically k plus 1 times sampling time t moment. As I said, this is k plus 1, right? And for tk, and this is, let's say, kt moment, right? Yeah. And when we write the discrete sequence numbers, and often in time, we don't have to write this capital T there. We can just write x of k plus 1 or x of k instead of x of kt, right? So then you look at this expression, what we have so far now. I can rewrite this one here as x of k plus 1 for this one here, and that's corresponding to this term, equal to sorry, this is small t, not small t. This is capital T, right? This is capital T. Capital T, capital T, capital T. So x of k plus 1 equal to e to the power ft times x of k. Okay, it's x of k here. And then I will keep this integral as detail, and g times u of k here. Okay, g times u of k. Good? Yeah. So it still doesn't look like a state space model yet, right? So now I'm going to let a equal to e to the power ft, and then let b equal to this whole ugly integral. Okay, yeah, times g also, okay, times g there. So if I do this, then you see I singled out this term and I singled out this term in here. Okay, yeah. So now that equation becomes a times x of k plus b times u of k. Right? This is exactly what we're looking for. This is a discrete state space model, right? This is a discrete space model here. And the A at here is related to the original continuous system F matrix by this equation, and B at here is related by this expression here, right? Yeah. So basically, if you have a continuous space model given, then the discrete model, 0 to whole equivalent, is this expression. A can be calculated with this, and B can be calculated with this. A seems okay, so this is e to the power ft, right? So we'll look at that later, because this seems to be alright, right? It's just the B still doesn't look about right yet, right? So let's look at the B here. We'll manipulate this a little bit, okay, to make more sense. So for B at here, we're gonna do a change of variables. So if you remember, when you do integral, there is a technique called change of variable, right? Yeah. So in this case here, we're gonna introduce a new variable we call lambda equal to tk plus 1 minus tau. So we're gonna use this one here. Okay. So if lambda equal to this, and d lambda will equal to negative d tau, right? Because the tk plus 1 is constant. Change a variable meaning you're going to have to change also the limits here, right? The limits, because see, tau goes from tk to tk plus 1. Okay? If I use the lambda, the new variable here, then what do? I'll replace the tau with tk, right? Replace tau with tk. So when tau equal to tk, lambda equal to tk plus 1 minus tk, which is equal to what? Capital T, right? The sampling time. When tau equal to tk plus 1 over here, then lambda equal to 0. Okay, so the limits change from tk to tk plus 1 to t to 0, right? And the integral here, the b integral, will become b integrating from t to 0, okay, e to the power of f, right? This is not this guy now, it's lambda. And then d tau, so you see d tau is equal to negative d lambda, right? So negative d lambda. And then times g, okay? Times g. So integral a to b is equal to negative b to a, right? So the whole thing, negative negative cancel, so this will be 0 to t e to the power f lambda d lambda times g. This is much better, right? Look at this one here, so clean. Okay, so and then your a is still the same thing. Okay, so a is still this, and then b is this. So everything will be computable now. Okay, so you can calculate if you're given f, if you're given g, and we'll be able to calculate this. So I'll show you how to do calculation. Okay, yeah. I think I'm going to stop here because we don't have time for the example now. So I'll show you an example in the next lecture. Okay? Yeah. Just a quick note about, remember I said I'm going to take you guys to the lab to get familiar with the equipment for the project, right? There's a little problem. It's actually a big problem. Because this year, the 477 happens the same time as our class lecture time. So they typically will have a full room over there. And given 40 students in the same room, I don't think they're going to allow us to do this at the same time. So I'm going to have to find a different time somehow. This is going to be a challenge, right? To have everybody there, and then for me to go over this, demonstrating this thing here, right? So I had to work it out with you guys as what would be a good time. It's not going to work for everybody for sure, right? How can we go to look at this equipment? Is that good? So let's talk about maybe next lecture or something next week. Okay? Yeah.